Hi, my name is Amelia, and I'll be presenting a look at some of the challenges and intricacies of the other domain that our team has explored, fine-tuning the large language model Llama 2 on the recipe domain. While there are a lot of datasets containing recipes available from the internet, we found that there was a lack of suitable question answering datasets that we could train our model on. Specifically, we wanted a dataset like Squad, which is a machine reading comprehension extracted QA dataset, designed to teach models to pinpoint answers within a text passage. Using the Squad format would allow us to take advantage of existing pipelines to evaluate the model for accuracy and efficiency. Squad is the gold standard, providing context-bound questions and answers. However, our recipe domain needed a custom touch, and well, with some napkin maths, it would probably cost $60,000 to hire enough crowdsourced workers to create Squad itself, time and resources we didn't have. Adapting 500 recipe batches from Recipe NLG, we engaged OpenAI's GPT 3.5 Turbo to generate a smorgasbord of questions. To extract precise answers, we upgraded to GPT-4. Though pricier, its accuracy justified the expense. If GPT-4's response matched the recipe text, it was indexed and stored in Squad format. After processing 2,500 recipes, we crafted a dataset of 2,242 entries. The entire process was faster and much cheaper, about $24 spent. For a dataset the size of Squad, it would cost $960 with this method, a far cry from $60,000. Now that we had our dataset, we needed to look into fine-tuning the models. The models that we have deployed are trained as causal language models, which generate text based on previous generated and provided text. But I looked into training the model as a proper extractive question answering model that specializes in strictly extracting the answer from the given context, by predicting where in the context the answer can be found. Evaluation results for these specialized models can be found in the report.
And I'll be presenting about the evaluation and deployment of our model in the cooking recipe domain. This presentation will cover approaches of prediction, metric use, results, and I'll also demonstrate our model. So there were two main prediction approaches used for our Llama 2 7 billion model. The first one, extractive QA, done by Amelia, tried to predict the answer's positions inside the context. The second method, causal LM, tried to predict the answer based on the given context and question. I will use an example to clarify the difference between the two approaches. So this is a recipe for the pumpkin cake as described in the context, with the question of how many eggs are needed for the pumpkin cake recipe. The answer is 4 eggs, as can be seen in the context. For the extractive QA approach, the model will predict the start and end positions of the answer 4 eggs inside the given context. Therefore, the prediction is a pair of integers. For the causal LM approach, the model will take context and questions in this format as input. Then it will try to predict the answer based on the given text. Therefore, the prediction is a string, something like 4 eggs are needed. After obtaining the prediction sets from the models, we use Hugging Face Evaluate library to calculate the exact match and F1 score metrics of the predictions in comparison with the reference answers. And here is the results we got for the model. For exact match, extractive QA approach with QLoRA technique had the highest score of 87.3%, which far exceeded the causal LM approach. For F1 score, once again, the extractive QA approach with QLoRA had the highest score of 93.5%, which was almost perfect. The causal LM approach also had good results of 76 and 71% for QLoRA and IA3 respectively. Further analysis of the results can be found in the report. Now let's move on to the deployment of our model. Thanks to the Gradio library, we could deploy our model to the Hugging Face very easily. As you can see, the user interface is relatively simple with the text box that allow user to type in the questions and context respectively. This model is the causal LM fine-tuned with QLoRA technique and it can be accessed through this link. And now I will demonstrate the model. As you can see here is the deployed model on the Hugging Face space. I will use the previous example of the pumpkin cake recipe. It asks for how many eggs in the recipe. Yep, 4 eggs, that's correct. Now let's change the question to let's ask it how many cinnamon are needed. How much cinnamon? It should output 2 teaspoons of cinnamon. Yes, 2 teaspoons, that's correct. Now let's use a longer context. Take this from the test datasets that we use to evaluate the model. It is about the grandma's cherry salad. The answer should be refrigerate until ready to use at least 3 hours. Let's see if it gives the correct answer or not. Refrigerate until ready to use at least 3 hours. Yes, that's correct.
Hello, my name is Chloe and I'm part of the biomedical sub-team that consists of me, Jianjia, and Karsh. And I'll be talking about our progress throughout the semester. So here we have the base model we use from MetaLlama, Llama 2.7b, that's hosted on Hugging Face. Next up, we have the dataset we use to fine-tune our model, which is the dataset that Jian had split of the CGP QA. And it's split into train, validation, and test. And this is done to standardize the training and evaluation progress. Next, Jen will be talking about the training fine-tuning script.
Hi, I'll be talking about the steps needed for the fine-tuning. So here is we're using the libraries, we're installing the libraries needed for fine-tune, and we're using 1DB. 1DB help us to keep tracking on the training that when the fine-tuning process is ongoing. It shows the evaluation loss and the training loss over here, which is important for us. And the reason here we're taking the notebook is because we need to bring in the MetaLlama 2 from Hugging Face, and also we'll push our final train model to our Hugging Face as well. Here, the bits and bytes config, we're using 4-bit, true, and NF4. It's the requirements for the QLoRA technique. Next, the important thing over here is we're using LoRa config, and the R parameters can be seen over here. It's the rank of the update matrix. So the low rank have a fewer trainable parameters. So here I'm using 32 and Chloe is using 16. So we have some difference. In terms of the datasets, I've already got 3 different splits, and here we are using the format needed to bring in the inputs datasets for the training purpose, and here we are using the format needed for the validation datasets. However, we just tokenize the train data and the validation data because 2 of this will be used in the training purpose. And here is the transformer. The arguments is over here, the transformer arguments. And the difference we did is I'm using 10 safe steps, which is it will create a checkpoint every 10 steps, and Chloe is using 5. We have some difference over here. And the maximum steps as well, I'm using 100 maximum steps and 150 maximum steps for me, and Chloe is using 100. Next, we just train it, and as we can see over here, it has 150 steps, and at the end we just push it to the model, push the model to the GitHub. Thank you.
Yep, so I'll be talking about the merging process. So after Jen has fine-tuned the model, it creates an adapter model. And here we import the adapter model from Hugging Face. and then we are merging it with the base model, and after it has merged, we are pushing it to Hugging Face as well. And the same thing goes for the tokenizer, which is pushed also to Hugging Face. And now I'll be giving a demonstration of both of our models, starting with Jian's first. So we use the context and the question that's the same for both models, and it provides us these output. And it is more detailed, as you can see. It specifies the details of the question and it answers the questions, but there's an issue with the output where it doesn't know when to stop generating text. And we tried to fix this problem by creating a stopping ID when generating the output, but it's not successful. However, I can say that the output of the model does answer the question to a certain degree that's acceptable. And then now I'll be looking at my model. So again, we use the same context and question, and it creates an output, and it's less detailed than Jian's model, but this is an expected pattern because my model has less logging steps and max steps when fine-tuning, and the R used is less, so mine's 16 and Jian's 32.
I would be talking about the evaluation result of our fine-tuned models. Our team focused on CGP-QA biomedical dataset, specifically fine-tuning the Llama 2 model to understand the impact of various hyperparameters on model performance. Looking at the numbers, comparing the two fine-tuned models, a significant improvement in the F1 score can be seen in compared to the base model. The base model has a F1 score of about 5, indicating a rather lack of exact matches between predictions and the actual labels. In contrast, the two models showed substantial enhancement, with F1 score of 19.6 and 20.08 respectively. This highlights the effectiveness of a fine-tuning process in improving the model's accuracy. It is important to also consider the exact score, which is 0 for the two models, indicating no perfect matches between predictions and ground truth tables was found. This could also be because the answer was worded differently, or different words or synonyms were used to mean the same thing. In very short, F1 score represents a balance between precision and recall, giving an overall measure on the model's accuracy in binary classification. The exact score, on the other hand, measures the exact matches between prediction and ground truth table, showcasing model's precision in providing accurate results. Lastly, perplexity score indicates the uncertainty in probability distribution, with lower values indicating a better predictive performance. With the two models, the perplexity score indicated a substantial improvement in the fine-tuning process. It was 2.32 for the base model, which went down to 1.64 and 1.44 for the two models. To sum up, the evaluation clearly demonstrates that our fine-tuning efforts led to a significant improvement in the F1 score, exact score, and perplexity score, ultimately enhancing the overall performance of our models and justifying the process of fine-tuning for this specific use case.